Hey guys, I'm doing question 90, which is on page 228 in the textbook. So the question is, suppose a star the size of our sun, but with a mass 8 times as great, we're rotating at a speed of 1 revolution every 9 days. If it were to undergo gravitational collapse to a neutron star of a radius 12 kilometers, losing 3/4 of its mass in the process, what would its rotational speed be? Assume also that the thrown-off mass carries off either no angular momentum or its proportional share 3/4 of the initial angular momentum.
So if we were to pick that no angular momentum is happening in this system, we could then assume that there's no external net torque happening, meaning that the angular momentum is being conserved. Then we can set up our conservation of angular momentum equation, which is L initial equals L final, L symbolizing angular momentum. We could expand the equation even more by using the angular momentum equation, rotational inertia times angular velocity.
So by substituting it in both initial and final sides, we get
this equation right here. And the next step we have to do is this what's in the box right here. And it's not really part of the equation steps from here to here. It's kind of separate because in the system itself, the moment of inertia is changing since the sun is being collapsed and its mass is decreasing and its radius is decreasing at the same time. So we have to account for that, which changes our rotational inertia. So even though we don't have any numerical values, we can always use that equation at the end with its changing masses, which they give us how proportionally it changes, to either cancel out or get to cancel out in the end. And since every celestial body is a sphere, usually, we can use the rotational inertia equation of 2/5 times m times r squared. And usually we are given this. So in the initial side, when the sun is pre-collapse and its mass is 8 times as greater than usual, we can always set it up here and put 8 times the initial mass, and we'll get 16/5 times mass times radius squared. For the final side, since it's after collapse, we're told by the question that it loses 3/4 of its mass, which is 2. It's 2 times as greater than usual. So if we would multiply that out, we'll get our final equation. Our rotational inertia final equation would be 4/5 times mass times r squared. So we'll plug that back in from here, so we will be able to manipulate it more to get our answer. So since our masses will cancel out in the end, we can get rid of those. And we can notice something special here, that 16/5 and 4/5 are proportional to each other by 4. So we can proportion those out, cancel these two out, getting this equation right here. 4 times r squared times the initial angular velocity equals r squared final times the final angular velocity. Since we are looking for final angular velocity, we need to figure out what these three variables, what their numerical value is. So for our final radius, we're given that it's 12 kilometers. So we can easily input that in our equation. And for our initial radius, we're given that we're not given it, but we can easily find out the radius of our sun online. And how we find our initial angular velocity is we have to do a few more extra steps. So in the equation, we're given our frequency. Our frequency is that its rotational speed is 1 revolution every 9 days. So basically it's 1/9 of a revolution every single day. So what I did, the extra step I did, was I just converted that into radians per second, which I got 8 1.08 times 10 to the negative 6 radians per second. So how I got that was, as my final thing is, in our textbook, we are given that frequency equals angular velocity over 2 pi. In our previous units, we've seen it as 1 over t. So if we reorientate that equation, we'll get angular velocity equals frequency times 2 pi. So when we do get that, we get this equation right here. And if we input that there, and we solve for frequency, our final angular velocity, we get this here, 1.07 times 10 to the 5th radians per second. The reason why I changed it radians per second was you could leave it at revolutions per day, but usually angular velocity is in radians per second. That's its units for angular velocity, so that's why I changed it. But you could always leave it in revolutions per day. So this is how you do question 90.